In this video, we're going to take a look at another variable that we're going to see quite often when we're dealing with gases, and that's temperature, because it does affect their behavior. So we're going to take a look at what temperature is and also see the different units of temperature and be able to convert between the different units. So when you use a thermometer to measure temperature, what you're measuring is essentially the average speed of the particles within uh, the beaker or the container or whatever you're measuring the temperature of. So we say it's the average kinetic energy, and kinetic energy is just really energy related to motion. So the average energy of movement within the substance, and so it's an average speed. Not all particles are moving at the same energy or same with the same energy of motion. Some are moving faster than others, so that's why when you take the temperature, it's an average speed of the particles. But essentially, in simple terms, when you have a low temperature, the average speed is lower than when you have a high temperature. So there's more kinetic energy in average. On average, there's more kinetic energy here when you're looking at temperature than there would be over here, assuming the same number of particles. So essentially, when your particles move faster, temperature goes up because you have a higher average speed of motion for those particles. So low temperature, low speed, low kinetic energy, in other words, and then high temperature. So if you heat this up, for example, particles move faster, and so there's a higher average kinetic energy here. So they're moving faster. And so to measure temperature, one common unit that you've used is degrees Celsius. That's what we use kind of in everyday life. So it's below zero, it's above zero, it's 0 degrees Celsius, it's 5 degrees Celsius, it's 15 degrees Celsius, it's negative 15 degrees Celsius. That's what you use, and that's what you see on the Weather Channel, if you live here. And so that unit can be used in certain circumstances. We can use it for some calculations, but when it comes to gas calculations and a lot of calculations in chemistry, we don't use the degrees Celsius anymore. We use what's called the Kelvin temperature scale. And the Kelvin temperature scale, it's a scale that will relate the kinetic energy directly, relate the temperature directly to the kinetic energy of the particles. The degrees Celsius scale doesn't necessarily relate to the amount of kinetic energy in your particles. It does, but not directly. It's more of a relative scale. Whereas the Kelvin temperature, if you have, for example, 100 Kelvin versus 200 Kelvin, what you can say is that the 200 Kelvin sample has 2 times the kinetic energy than the 100 Kelvin sample. So it's a direct relationship like that. But you can't really say that with degrees Celsius. It's not a direct relationship like that. With degrees Celsius, you could say, 15 degrees has more kinetic energy than 5 degrees, but it's not necessarily 3 times more because it's not a direct relationship. So to get that more direct relationship, we use the Kelvin temperature scale. And the Kelvin temperature scale is convenient. Well, first of all, because it gives you a direct relationship between the temperature and the energy, but also it's convenient because you don't get negative numbers with Kelvin. The Kelvin scale does not have negative numbers. The lowest temperature you can get for Kelvin is actually 0 Kelvin. If you were to convert that to degrees Celsius, it's negative 273.15 degrees Celsius. And this temperature is a special name. It's called absolute zero. And I put a video here for you to watch if you'd like, but it's the lowest possible temperature. It's where there'd be essentially no motion or minimal motion. In reality, when you have very, very low temperatures, you still have motion. You have vibrational motion that's happening. There's still movement there. But at this temperature, theoretically, you'd have no motion and no heat at all. So that would be called absolute zero. And we haven't really reached that because in any lab that you have, you always have some kind of heat transfer happening that would transfer to the particles in the area you're trying to get to absolute zero. But the main point is that Kelvin's lowest temperature is 0 Kelvin, and there's no negative numbers. So it makes our calculations much more convenient. So there's a direct relationship with the amount of the kinetic energy and the Kelvin temperature, unlike the degrees Celsius scale. And there's also no negative numbers, which is more convenient for calculations. So to convert to Kelvin, you simply do your degrees Celsius plus your 273.15. And to convert from Kelvin to degrees Celsius, you do Kelvin minus 273.15. So if you remember those conversion formulas, it's going to be pretty straightforward to convert because it's a simple addition. So this is just a thermometer, two thermometers comparing the Kelvin scale to the Celsius scale. So if we have our negative, here we have our Kelvin scale. You'll notice we only have positive values, whereas here we have our Celsius scale. And so we have a 0 mark, and then the 0 mark, you can go below 0 and have negative values, and above 0 and have positive values. But essentially, our Celsius scale is sort of based on that the water freezing point and boiling point. So you can see here, for example, that 0 is when water freezes, 100 degrees Celsius is when water boils. So it's all relative to that. And then below 0 is well below freezing, and then above 0 as well above freezing. And here's your water's boiling point. And you can see there's a relationship between them there as well. And then absolute 0 would be 0 Kelvin, which is the lowest temperature you can get. And then that would be negative 273.15 degrees Celsius. So what do I mean by Kelvin relates directly to the kinetic energy? Well, if you look over here, suppose you had a Kelvin temperature of 2 and your kinetic energy was 2. Well, you could double the Kelvin, so 4, and your kinetic energy would be 4. So there's a direct relationship between the Kelvin temperature and the kinetic energy, which you don't quite see in the degrees Celsius, because degrees Celsius is sort of based on more outside observations, like when does water freeze, when does water boil, and we'll give those temperatures, we'll give those numbers as the temperatures for Celsius. So it's more of a relative scale, whereas the Kelvin scale gives you more direct relationships with the amount of energy and the temperature, and also there's no negative values. And then where does that absolute 0 come from? Well, here we have temperatures in degrees Celsius, and that's on the x-axis. And on the y-axis, we have our volume. And so we have these temperatures and volume plotted here. So we have our 4 different pressures at pressure 1, pressure 2, pressure 3, pressure 4. But what I want you to notice is that if you extend all of these different lines here, they'll all eventually meet up at a point where the volume is 0. In other words, where there's no movement, there's 0 volume, everything is condensed to a point where there's no movement anymore. And that point they all converge onto is negative 273.15, which we call absolute 0. You're not going to have a negative volume. Essentially, 0 is the lowest volume you could theoretically get, and that's where we get absolute 0 from. So these are all different pressures. You'll notice that as we decrease the volume, so going from right to left, decrease the temperature as we go from right to left, the volume goes down. So we have a lower volume. And then again, if you just extend the lines behind, you'll see they all converge until the 0 point over here. And that 0 point is negative 273.15 degrees Celsius, or 0 Kelvin. And that's where absolute 0 comes from. Again, you're not going to have volume less than 0 in the negatives. So let's take a look at how to convert for different temperatures. To go from Kelvin to Celsius, and then Celsius to Kelvin. And it's simply following these formulas over here. So let's do some sample problems together. After we do sample problems, a couple things I will mention to you are how to convert your volumes, because volumes are also a variable in gas calculations. And then also we're going to take a look at some standard conditions which a lot of the reactions happen at. So let's go do our temperature calculations to see if we can do some unit conversion. So again, we saw a new temperature scale. First of all, we saw that temperature is the average kinetic energy in a sample. And so when the particles move faster, your temperature is higher. And when your temperature is lower, it's because your particles are not moving as fast. Now we saw that in gas calculations, we're not going to use a degrees Celsius scale anymore. We want to use a scale that's more convenient, that doesn't have any negative numbers, and also allows us to make a direct relationship to the amount of kinetic energy in the particles of that sample. In the Kelvin temperature scale, the lowest value you can get is 0 Kelvin. If you were to convert that to degrees Celsius, that's negative 273.15 degrees Celsius, which is essentially something called absolute 0, where there's no more movement or heat. It's your minimal volume and minimal motion. And we saw a chart that shows us how we determined where the absolute 0 would be at what temperature in the slide deck. So we do need to remember that we want to convert from degrees Celsius to Kelvin. We simply add 273.15, and that will allow us to convert our temperature values. Just again, this chart over here, this graph over here illustrates the direct relationship between Kelvin and kinetic energy. So I'm just making up a value here. If my Kelvin temperature was 2 and my kinetic energy value was 2 over here, then if I doubled my Kelvin temperature to 4, then I'm also doubling my kinetic energy here. With degrees Celsius, it doesn't quite work that way. So if you have 15 degrees Celsius and 30 degrees Celsius, you can't assume the 30 degrees Celsius sample has doubled the energy, because it's not based on the amount of kinetic energy directly. It's more based on that level of where does water freeze and where does water boil. So it's a more of a relative scale when it comes to degrees Celsius. So it's always nice to have a better direct relationship with your units, and that's what the Kelvin scale allows as well. So here we have our first question. SATP, and I'll teach you what that is later on, occurs at 25 degrees Celsius. What is the temperature in Kelvin? So we want to go from Celsius to Kelvin. So we know our Kelvin temperature is going to be our degrees Celsius plus 273.15. So that's going to be our 25 degrees Celsius plus 273.15. And so we'll get, if you do 25 plus 273.15, 298.15 Kelvin. 298.15 Kelvin. And make sure you put that unit like that. Now, if this was just a one question, one-step question, you could also go to your correct number of sig figs. So since you're adding here, the smallest number of decimal places would be 0 decimal places, so 298 Kelvin. If this was a question with multiple steps, just keep all the decimal places in and just round at the very end. But that's to our proper number of sig figs. So now we'll try this next one here. You can pause the video and try it yourself. We have 27.3 degrees Celsius, and we want to convert it to Kelvin. So same idea. We know Kelvin is equal to degrees Celsius plus 273.15. So that's going to be 27.3 degrees Celsius plus our 273.15. And we're going to get, so 27.3 plus 273.15, 300.45 Kelvin. We're going to keep one decimal place since that's the smallest number of decimal places there. And we'll get 300 point. There's only a 5 after, so remember it rounds down to 4 to keep it even. 0.4 Kelvin. And that there is our Kelvin temperature. Now we're going to go the other way around. We have Kelvin and we want to go degrees Celsius. So if you want to convert to degrees Celsius, you do your Kelvin temperature minus 273.15. Now, you'll never have a negative Kelvin, but you can have negative degrees Celsius. That we know because we deal with degrees Celsius all the time. And so for Kelvin, we're going to do 23.5 Kelvin minus 273.15. So 23.5 minus 273.15. And we get negative 249.65 degrees Celsius. And if you want to round it to the correct number of sig figs, just one decimal place there, negative 249.6 degrees Celsius is our temperature. So we're not quite at absolute zero. We're getting pretty close to that, but we are still very cold nonetheless. And so we kept the proper number of sig figs because we did a simple subtraction. We had one decimal place here. In reality, though, you're not really just going to do conversions for temperatures for no reason. You're usually going to do a conversion so you can use it in a problem that has a few more steps. And so you keep all your decimal places until you get to the last step, as we typically do in our questions. So in this video, we saw what temperature is, and we saw the new scale called the Kelvin scale, which we'll be converting to quite often for gas calculations. We also saw why that Kelvin scale is quite convenient on a few levels, such as no negative numbers and also having a direct relationship with the kinetic energy in the particles. In the next video, we're going to take a look at volume and volume conversions quickly, and then take a look at some standard temperatures and pressures that you should remember for problems going forward.